They say that a picture's worth 1,000 words. This is definitely true for spacetime diagrams in relativity. You understand these, you can derive everything else you need, which is what we'll do in this video. They're easy enough to draw. You just put a time axis on the vertical and fit as many space axes as you can manage to draw on a two-dimensional piece of paper, so usually stopping at 1. We will start with the relativity of simultaneity by placing observers and drawing light rays. Then we will use this to derive the Lorentz transformations and all their effects of time and length contraction. We will need 3 friends, Alice, Bob, and Charlie. Let's first have them stand a distance L away from each other. To test whether their watches are synchronized, they agree to wait until their watches hit 12 noon and then send light pulses towards Bob, and let's say that this picture represents t equals 0. How do we draw this on the spacetime diagram? Well, by convention, light beams are always drawn so that they are at a 45-degree angle. So this line over here is x equals ct. You can think of this as using natural units where c is equal to 1, which we won't do in this video. Instead, think of it as just rescaling your diagram so that light gets this slope. So the units for the time axis would have to be 1/zillionth of a second. The rays of Alice and Charlie then look like this. If Bob receives them at the same time, it means that Alice and Charlie have perfectly synchronized watches. Well, you know what's coming next. We will put them on a train that is moving at a constant velocity. That's an inertial reference frame, and the principle of relativity says that the laws of physics are the same in all inertial reference frames. So on the train, the experiment has to conclude exactly the same way, and Bob again catches the 2 pulses at the same time. But let's add a 4th observer now on the ground. Let's call her Denise. The train is moving relative to her, so her point of view might differ. So let's say that this picture is t equals 0 again. So Denise and Bob are aligned on the x-axis, going this way at t equals 0. Now, according to Denise, Alice, Bob, and Charlie's positions are changing with time. So they are all going to follow these sloped trajectories on her spacetime diagram. Alice will be on this line x equals vt, Bob will be on x equals vt plus L, and Charlie will be on vt plus 2L. So what will the light pulses look like when they originate from these trajectories, emitted by moving observers? Well, recall that the second postulate of special relativity requires that the speed of light be measured the same constant in all inertial reference frames. What does that imply on the spacetime diagrams? Well, the 45-degree angle of the light rays must be universal. They're the same for all observers. So it doesn't matter that Alice and Charlie are moving while they emit their light beams. Denise will still draw them on her diagram like this. So let's start with the assumption that Denise also sees the beams emitted simultaneously. Well, we can see just by drawing Charlie's pulse that if this is the case, they wouldn't land on Bob's trajectory at the same time. But that can't be true. We know that Bob receives them at the same time from the principle of relativity. There shouldn't be 2 points associated with Bob catching the pulses on Denise's spacetime diagram, while there is only 1 on the train. Now, this is an important point. All observers need to agree on what actually happens at a specific moment in time. That is a specific point in spacetime called an event, and events are Lorentz invariant. Let's imagine a different scenario to see why this has to be true. So imagine again that Bob is on a train, and let's say it's walled off this time, and Bob reaches out of a window here with his extra long arm, then Denise reaches up from the ground. After some time, Bob gives Denise a high five. Now, this is an event, and while it may not be a good idea for either of them to remain in good health, high fives are possible even if the train is moving at relativistic velocities, right? So no matter how fast or slow their clocks are ticking, or how out of sync they are, or how much their lengths are contracted, the physical fact is Their hands were at the same point in space at the same time, and no reference frame can disagree on that. This, by the way, is also why we are able to put an origin onto our spacetime diagram. All observers agree that some point is t equals 0 and x equals 0. Where relativity happens is in between the events, just like how music is the space between the notes. So the event in question here that everybody must agree on is Bob catching both light rays at the same time. Well, for Denise to see this happen, Charlie's beam has to intersect Bob's trajectory at the same time as Alice's does. So what she sees is this. At t equals 0, Alice first emits her beam, but then Charlie emits his a little later. They are not synchronized. This is because Bob moves away from Alice's beam and towards Charlie's beam, while the light beams are not affected by their emitter's movement. Alice's beam takes longer to reach Bob than Charlie's does, but he catches both at the same time, so they couldn't have been emitted simultaneously. For more details on this, be sure to watch the previous video on simultaneity. The relativity playlist will be linked everywhere. Now then, we have obtained a really important line to draw on the spacetime diagram. This blue line marks the set of events that are simultaneous with the origin on the train frame. So this is all the points in spacetime where they measured that t is equal to 0. In other words, this is their x-axis. Let's call it x prime so we can tell them apart. Now notice that it starts to get further and further from Denise's x-axis, so what is simultaneous according to the two reference frames differ more and more the further you are from the origin. Now we already have another line. This x equals vt line that we drew earlier happens to be the set of all points in time where x is equal to 0 for the train frame. This is their t prime axis. This is the essence of a Lorentz transformation. The two reference frames have different coordinate axes, so their observers assign different coordinates to the same events. And now we have everything we need to derive these transformations. Let's start by talking more about the t prime axis, which will give us the first one. So x prime equals 0 we can think of as the back of the train, right? It's where Alice is standing on our spacetime diagram. And of course, this point is moving relative to Denise such that its position is x equals vt. Now for the train observers, the back of the train is at rest. They keep it as x prime equals 0. So to transform between these coordinates, we say that x prime is equal to x minus vt. This is basically the train people saying to Denise, well, whatever x it is you measure, just subtract all that v times t nonsense, because the back of the train is at rest, it's not moving. And that's our primitive transformation. So if they were to measure Bob's position instead, on the train frame it would be x prime equals L, but on the ground frame it would be x equals vt plus L. Now this is what is called a Galilean transformation, right? This is not relativistic. So I can hear you screaming at the screen, where is the gamma, where is the Lorentz factor, none of this is right. And yes, you're absolutely right, we are about to get there, but I want to actually motivate and see why we need the factor of gamma. So first let's also talk about the time transformation. According to the Galilean transformations, of course, time is universal, so t equals t prime. But we can see on the spacetime diagram that this is not the case. So what we really want to get is the slope of this new t prime equals 0 line that we drew down here. Well, since it's a line, we just need an equation for just one point on that line, like where Charlie is standing over here. Let's call that point Q, and then call this point up here, where Bob catches the light beams, P. By using what we have so far, we can make up some equations for these 2 points, and that will allow us to get a slope for this x prime axis. Now at this point in the video, we're going to have to do some algebra. It takes a little bit of time, but everything actually cancels out, so you can either follow along or even skip this part if you want. But whatever you do, don't worry about the factor gamma. I promise we'll get there after this. So, let's start with the point P. There are two of these lines that we already know about that intersect at the point P. We have the line x equals ct, and then the line x equals vt plus L. Well, if they intersect at P, all we have to do is write both of these equations together to get the x and t coordinates for the point P. So we can write down x equals ct into this equation x equals vt plus L. That gives ct is equal to vt plus L. We can go ahead and call the t Tp, and if we factor the c minus v, it is equal to L. So Tp is equal to L over c minus v. Well, we know what Tp is. Now we can write it into x equals ct, and we get xp is equal to this just multiplied by c. That's cl over c minus v. Those are the coordinates of the point P. So how do we do this for the point Q now? Well, we have two lines passing through there again, but we don't know exactly what the light ray equation is. It has to be x plus ct equals a constant, and then that is going to intersect the line x equals vt plus 2L. So we just have to figure out what that constant is. Luckily, that same line also passes through the point P, and we already know the coordinates over there. We can find what the constant is by just plugging in the values of x and t at the point P. So we can just sum them up. If we go ahead and multiply the second parenthesis by c, well, they are the same thing. This just turns out to be 2lc over c minus v. So that is the constant. Let's go ahead and write that into its equation, and we can erase all of this. So let's plug this x equals vt plus 2L into the new equation that we found. So that gives us vt plus 2L, that's the x here, plus ct is equal to the new constant we found. Let's call these t's tq. And if we factor all of this, we get v plus c times tq is equal to 2lc over c minus v minus 2L. We have to multiply that minus 2L by c minus v. So we get the right hand side, 2lc minus 2lc plus 2lv. Those LC's cancel out, and we get that TQ is equal to 2LV over C plus V, C minus V, that is C squared minus V squared. Okay, now to find X, we can use this equation again. So XQ is equal to V times TQ plus 2L, that is 2LV squared over C squared minus V squared. And then we get the LV's canceling out. And finally, we get xq is equal to 2lc squared over c squared minus v squared. Okay, is that gamma factor coming? Don't worry, it is coming very soon. For now, let's just go ahead and get that slope. So we can divide tq by xq, and we get the c squared v squareds canceling out, and the final answer is v over c squared. So for this line, we have the equation t equal v over c squared x. This is all we wanted from this algebra, because now we have the equation for the x prime axis that we drew on our spacetime diagram. So we have t prime, where x prime is equal to 0, and we already have the Galilean transformation for this, so x prime equals x minus vt. Now we have the x prime axis, and now we also have a transformation for this. T prime is equal to t minus v over c squared x. That is the slope that we just found. Okay, now ladies and gentlemen, the moment we have all been waiting for, let's introduce that famous Lorentz factor. Let's start by discussing why we actually need it. Well, there is something we have to test here. Is this transformation right? If it is, it has to satisfy the principle of relativity. So this is going to be a test of symmetry. A symmetry implied by the principle of relativity. What is it? Well, we know the transformations that go from x to x prime, right? From the ground frame to the train frame. Now with these transformations, there's kind of a preferred frame, right? We're going from the ground to the train. We should just as easily be able to go from the train frame to the ground frame. So we also want the transformations to work backwards without a preferred inertial reference frame. The only difference between them can be the sign of the velocity, because according to the ground, the train is going forward. According to the train, the ground is going backwards. So we want to have x equals x prime plus vt prime. And similarly, t is equal to t prime plus v over c squared x prime. And these transformations need to cancel each other out. So what we can do is insert one of these into the other and see if we get back to where we started. Well, let's do that. X prime is equal to x minus vt, and into this we want to insert x is equal to x prime plus vt prime, and then t is equal to t prime plus v over c squared x prime. Let's go ahead and put these into parentheses so we don't confuse them. Let's go ahead and multiply the v into that second parenthesis, and we get the x primes canceling out, we get the vt primes canceling out, and in the end we get, drumroll please, v squared over c squared x prime equal to 0. That's a disaster. That doesn't work. Well, it's not a complete disaster because we may be able to add a factor to these equations to actually make them behave well with the symmetry. And we know that it has to be a function of the velocity and the speed of light, as those are the only invariant quantities that we have right now. Anything else would make the transformations non-symmetric. So let's try our new transformation. We get x prime equals gamma x minus vt, and just like before, let's insert x equals gamma times the previous transformation and t equals gamma times the previous transformation. So let's factor the gammas out first and open up a parenthesis here. And let me just write all the inserted transformations in orange. Okay, so we have a common factor of gamma on both of them. Let's factor that out too. And we get gamma squared x prime plus vt prime. And then if we go ahead and multiply this v in here, we have minus vt prime minus v squared over c squared x prime. Okay, once again the vt is canceling out. And now we also have a common factor of x prime inside here, so we'll write that outside. We get 1 minus v squared over c squared with the x prime outside. Now, we already have the x prime on the other side, so those are going to cancel out. And then we can just solve for gamma by dividing everywhere by this parenthesis. So we get gamma squared is 1 over 1 minus v squared over c squared, and gamma is 1 over the square root of 1 minus v squared over c squared. So there we finally have it, the famous Lorentz factor. This is the final piece of the puzzle for our Lorentz transformations, because now they satisfy everything we see on the spacetime diagram, and they satisfy the symmetry required by the principle of relativity. There are more mathematically rigorous ways to do this, but if you think about it, all we have done is invoked our postulates and satisfied everything we see on the spacetime diagram. And I think it's always nice to obtain something by using an argument of symmetry. Okay, so now let's see how these work, and as promised, we're going to get length contraction and time dilation. And let's draw them on our space-time diagram so we can keep seeing it all happen. So let's say that a measurement is made on the train and they get a distance L prime as a result. Maybe it's Bob measuring the distance between Alice and Charlie, and in their frame he measures both ends simultaneously, say at t prime equals 0. So this L prime has to be on the x prime axis that we drew on our spacetime diagram. Now the x prime and t prime coordinates of this point is L prime and 0. Just by drawing this on the diagram, we see that even though the measurement is made simultaneously on the train, it is not made simultaneously as seen by Denise. But let's say that Denise also measures the distance between these same 2 points, but she does it according to her t equals 0. Well, that would just be the projection of this line down to here onto Denise's x-axis. So the xt coordinates of this point would be, let's say, L and 0. So what we want to do is use our transformation between the coordinates to find how L is related to L prime. Which transformation are we using? Well, we want to go from the train coordinates down to the ground coordinates. So from the prime to the unprimed coordinates. So we have to use this one. Now x prime is L prime and t prime is 0. So from here we just get L equal to gamma L prime. Okay, so let's think numbers. This factor of gamma is always greater than 1 because the speed of light is always greater than v. Just to make it easy, I always think that this square root of 1 minus v squared over c squared is equal to 0.5, so 1/2, so that gamma is equal to 2. For this to happen, you need your v to be something like square root of 3 over 2 times c. And so we get that L is equal to 2L prime. L is larger than L prime. What this means is that if Bob is standing inside the moving train and measuring how long the train is, and let's say he finds 10 meters, Denise looking from the outside is going to see the train and indeed Bob inside it squished down to 5 meters. This is length contraction. Hooray! The train looks thinner. Well, this is a great way to demonstrate length contraction if you want to miss the whole point of length contraction. What is way cooler is when you look at it from the train frame. So let's look at the same setup, but this time instead of measuring the train, let's measure the amount of distance to destination. So the amount of road that they have ahead of them. Let's say that Denise measures this distance to be 100 kilometers from the outside. Now the frame that is moving relative to the observer gets length contracted. If we look at Bob's point of view, it is the ground that is moving relative to him. What does this mean? It means that he measures the same distance to destination to only be half as long. He measures 50 kilometers instead of 100. Now that is useful. When you go faster, not only do you go faster, but it's as if your destination just comes closer to you. It's crazy. The road is contracted. So, excitement aside, what's confusing about this, of course, is, well, how do they agree on how long it takes for them to travel there? Bob claims that he is only traveling 50 kilometers while Denise measures 100 kilometers, and they both measure the same velocity because that velocity is relative to each other anyway. How does this not cause a paradox? Well, this is where the complementary effect comes in. Time dilation. Sorry to do this, but for the purposes of time, I'm going to leave it as an exercise for you to get the relation between t and t prime. We can use a similar transformation to do it, and we get that t again is equal to gamma t prime. So once again, t prime is smaller than t. What does this mean? Well, if we have gamma equal to 2 again, it means that every time 2 seconds pass on the ground frame, Denise is going to see that only 1 second passes on the train frame. So for every tick that Denise sees on Bob's clock, she sees 2 ticks on her clock. So this is how they agree. Denise says that Bob has traveled 100 kilometers to reach his destination, so he takes time t, but she also knows that Bob's clocks are ticking half as quickly. That means that she agrees that Bob's watch is going to measure only half the amount of time has elapsed as Denise's watch has measured. Bob, on the other hand, thinks that, well, my clocks are ticking normally, that's the principle of relativity, right? But now the road is length contracted, so I only travel for 50 kilometers. So Bob also agrees that the time elapsed on his clock is 1/2t. Now there is something important that we need to talk about, which might be bothering you. This is a geometrical problem. We have found that on these spacetime diagrams, always these x prime axes and the t prime axes are the smaller lengths. But that does not fit our intuition at all, because that is the hypotenuse of this triangle. So how can L prime be shorter than L? It's supposed to be longer. Well, this may at first seem like a mistake. It's not. And it's not a simple question with a simple, tricky answer. It is actually a very deep, very profound, and very mathematical concept. We have to ask the question, how do we define a distance in a mathematical space? Well, it turns out that it is done through a structure called a metric. What is a metric? Well, very roughly speaking, on our usual Euclidean geometry, we can think of the metric as the Pythagorean theorem. This equation is precisely the reason why we expect for L prime to be longer than L. But it turns out that on flat spacetime, we use a different metric. It's called a Minkowski metric. And here, a distance is actually defined as x squared minus c squared t squared. So with a Minkowski metric, you actually take the difference of these two coordinates. So what this means on the spacetime diagram is that as you draw lines that get closer to this x equals ct, as you get closer to a light beam on a spacetime diagram, your lengths become shorter. So these orange lines that I've drawn here, and these would belong to a reference frame that is moving very fast relative to these two. If we go ahead and project down these points, and by the way, how do you project things down when your coordinate systems are oblique like this? Well, you still have to draw a line that is parallel to your t prime axis to project down to the x prime axis. And then you draw one parallel to your x prime axis to project to the t prime axis. So all of this and more will be on the next video. We are going to dive deep into the geometry of these spacetime diagrams. And once we master them, we're going to be ready for anything that relativity can throw in our way. So thanks for watching, and I'll see you there.